assignments, doubts, exams. We have got you back. EduPlanner make every chapter easy to understand. Stay tuned, learn more, grow with us.
Here we have an alpha particle that's brought in surface proximity to a Fermi particle. And we are supposed to find what the maximum kinetic energy it would be of the alpha particle as it approaches infinity, as it speeds away from the repelling force of the Fermi particle. The alpha particle is the nucleus of a helium atom. It has a atomic number of 2, an atomic mass number of 4. It has a positive charge of plus 2e. The Fermi atom has an atomic number of 100 and an atomic mass number of 257. To do this problem, we're going to have to know how far apart their centers are from each other when they're in contact. And I'm going to call this distance script r as the sum of the radius of the alpha particle plus the radius of the Fermi atom. Next, we'll need to calculate each of these radii using our formula 30-1. That can be done as follows. 1.2 times 10 to the negative 15th meters times the cube root of the atomic mass number for the alpha particle, which is 4. Cube root. Similarly, for the Fermi element atom, the radius of that nucleus has this same scaling constant times the cube root of its atomic mass number, which is a much larger 257 cube rooted. Okay. the next step here is to figure out what these respective potential and kinetic energies will be as the alpha particle approaches infinity. That is, our script R approaches infinity here. Well, at that point, the alpha particle will have complete kinetic energy. It will have no potential energy, as opposed to the starting point here, where the two particles are close to touching, they're at rest. Here, the system is in a state of complete potential energy, which we're going to denote as PE naught. For the case of kinetic energy, as it approaches infinity, all of the potential energy that occurred in this state with the particles touching is going to be transferred to the alpha particle as it moves, approaching that infinite distance. So the critical concept we need to take home in order to progress with this problem is that the kinetic energy at infinity is equal to the potential energy at this initial state. So that means we're going to need to find this potential energy in the initial state here. So to do that, we need to note that the potential energy of charges at rest from electrostatics, the equation for that is, well, the equation we should start out with is potential energy at rest initially is equal to the charge times the voltage in the given off by the Fermi atom in this case. That doesn't tell us much. We also need to know what this V sub naught is, the initial voltage. It is proportional to the charge of the system here, in this case, the Fermi atom, over the distance of separation. And that's what we defined here in terms of the sum of radii of the respective particles. From this, we can infer, or rewrite the equation, rather, that the initial potential energy is this proportionality constant, we'll get into that in a second, times the charge of the big particle, the Fermi atom, times the charge of the alpha particle over the distance separating their centers, which we're going to write here as R sub alpha plus R sub Fermi atom. Plugging in these constants, we note that the constant of the proportionality constant here for electric voltages in this unit system, that is, not SI, we have 9 times 10 to the negative 9 times units of Newton meters squared over Coulomb squared times our two charges, one of which is 2 E for the equivalent positive charge of an electron, and 100 E. That's for the alpha particle, that's for the Fermi atom. That numerator is over the following denominator, which we can write as 1.905 plus 7.629 that quantity times 10 to the negative 15th meters leaves us with, if you plug those in, I believe you're left with an intermediate quantity here of 18.0 times 10 to the 11th Newton times meter squared over Coulomb squared times these units of electron charge, positive electron charge squared over 9.53 times 10 to the negative 15th meters. Now we need to pay special attention to our units here. And we want to end up with an answer in electron volts. So the conversion factor for that is 1.6 times 10 to the negative 19th coulombs per amount of electron charge times this quotient here, 1.89 times 10 to the 26th. And these turn out to be voltage over Coulomb times our amount of electron charge. You can see that if, that electron cancels with one of those, this Coulomb charge cancels with that Coulomb on the bottom, and this turns out to be 30.2 times 10 to the 6th electron volts, which matches the answer in the back of the book. The electron, as it approaches, I'm sorry, it's not an electron, the alpha particle, excuse me, as it goes from contacting the Fermi atom to infinity, is equal to 30 mega electron volts, dropping down to two significant figures. And that's our answer.